Welcome. The topic we'll be discussing in this lecture is addressing modes. So basically, what is an addressing mode? The addressing mode specifies the location of the operand. Okay. So there are different formats of addressing. So depending on the requirement, we may have to use the appropriate format of address. And in different addressing format, the place where the operand is located might be specified in different ways, and that is what we call it as addressing modes. Okay, so addressing mode is basically the ways in which the location of operand is specified in an instruction, right? Okay, so addressing mode is nothing but it specifies the location of operand in a given instruction, right? So let us discuss the commonly used address modes in a typical processor, right? So this table actually it gives a brief overview about the commonly used address modes. So these are the various commonly used address modes, which are immediate address modes, immediate address mode, register address mode, absolute or direct address mode. Absolute address mode is also called as direct address mode. Indirect address mode, or it is called as, so there are two types of indirect addressing. One is register indirecting, another one is memory indirecting address mode. Okay, and then index addressing mode, base with index addressing mode, base with index and offset addressing mode. So basically this type of this indexing addressing mode we use when we want to access an array. So all these things basically come under one category. It is used when we want to access an array, because array will have index location. First you want to access the element of the 0th location, then first location, and second location, so on and so forth. And then there is something called as the relative addressing mode. Okay, this is connected with PC, program counter. Program counter always points to the address of the next instruction to be executed. But from the program counter, if program counter is currently pointing to 2000, okay, but if you want to execute due to some reason, if you want to execute the instruction which is located at 2008, okay, then this x you have to process to 8. Okay, it will add the content of program counter. Program counter is 2000, x is 8, so 2000 plus 8 is 2008. So the effective address will be calculated like that. Then the instruction at location 2008 will be executed. So you are executing an instruction which is relative to the content of program counter. Okay, so this is called as relative addressing mode. And then there is something called as auto increment and auto decrement, which is similar to the post increment and post decrement in C or Java. So auto increment is nothing but it is post increment, whereas auto decrement is a pre decrement, right? So these are the various addressing modes in brief. Let us discuss in detail how all these addressing modes works. Okay, fine. So let me give so if you see immediate addressing mode, we give some immediate value. Whenever you give an immediate value, you have to specify a hash symbol before that. Okay, so it means it represents that value. Okay, for register addressing mode, we directly use some registers. So effective address will be calculated based on the register values. For absolute address mode, we directly specify the memory location by using some location address, right? Whereas in indirect addressing mode, the memory location will be indirectly specified through some registers or through some address that we will discuss how it works, right? And as I already said, all these three, index, base with index and offset, are used for accessing arrays. Okay. And relative address is when you want to access some instruction which is relatively at some other distance from the program counter. Auto increment and auto decrement, which is equivalent to post increment and pre decrement, right? Okay, fine. So let us start with in the table there is one addressing mode which is missing, which is called as implied addressing mode. The one addressing mode that is missing in this table is implied addressing mode. So first we will discuss what is implied addressing mode. Okay, after that we will discuss all the other addressing modes, right? We may not strictly follow this order, but more or less we'll follow this table order, right? Okay. So the first thing what we'll be discussing is implied addressing mode. So implied means it is something like implicit. You are not explicitly telling. It is implicitly, it means that. Okay. So it means directly we are not telling that some register or something is involved in this addressing, but actually it is understood. Okay. So implied, basically it is similar to implicit. So implicit means what? It is not explicitly specified. It is implicit. It is understood. It is something like that. Okay. So here are some examples for implied addressing mode. Previously we have discussed one address instruction. Assume you are giving an one address instruction of this format: add yum within square bracket AR. So AR means some constant value. Say for example, if I give add if I add yum of 4. Okay, here yum represents some memory location. Yum represents some memory location. Okay, some location in memory, right? Fine. If yum is 1000, then it means that add 4 with 1000. Okay, it means that add 4 with 1000 if it is a byte address. If it is a, if the word size is 1 byte, if the word size is 1 byte, it will add just 4 with yum. Okay, if the word size is 2 bytes, even though if you give here 4, actually one word size is 2 bytes, so it will add in that case it won't add just 1, rather it will add 2. Okay, because we are not, because here word size is 2 bytes, right? So it will add yum plus, if the word size is 1 byte, it will just add yum plus 4. Okay, if the word size is 2 bytes, okay, it will add yum plus 4 into 2, that is it will add 8 bytes. Are you getting? Yum plus 4 into 2, yeah, yum plus 4 into 2, that is it will add 1000 plus 8, so 1008 location it will access. Okay, if the word size is 3 bytes, it will add yum plus 4 into 3, that means 4 3s are 12, then it means that it refers to the memory location 1012. Okay, so that depends on the word size. For simplicity, for understanding purpose, let us assume the word size is 1 byte only. Okay, that is each instruction occupies only 1 byte in the memory, right? So yum plus 4 means it refers to the address. Yum is 1000, yum plus 4 is 1004, so it refers to the location 1004. Okay, it refers to the location 1004. Now what does it mean add 1004 means what? Already we have discussed. So where it will be added? This is a one address instruction, so the value at this location, say the value at this location is 24, then this will be added with the content of accumulator. This will be added with the content of accumulator. Okay, let us assume accumulator contains 10, then this 24 will be added with 10, and the result will be stored in accumulator, and now accumulator will be updated to new value of 34, right? So why we are calling this as implied addressing? Because here accumulator is implied. Here we are not, in the instruction are we specifying directly the name of accumulator anywhere? No. So this is called as implied addressing mode. Okay, accumulator, the name accumulator is implied, it is understood, right? Okay. Similarly, there is another example. In the previous class we have discussed an example for zero address instruction, add. So when you give just add, what will happen? The content of TOS and TOS minus 1 will be popped out. Whatever the, if this is the top of stack and this is TOS minus 1, if this is 4 and this is 7, then these two items will be popped out and they will be added. 7 plus 4 will be 11, and that will be again popped in this location, and that will be popped as the new top of stack. Okay, so here also, does this instruction anywhere talks about TOS? No, it is directly in the instruction. We are not at all using the term TOS. But whenever you use the zero address instruction, it actually TOS is involved. So TOS is implied here. So such addresses are called such instructions comes under implied addressing mode, right? Okay. Next is immediate. It's very simple. In immediate addressing mode, we directly give some immediate value. We directly give some immediate value. So here, this is an example, move R1, 5. So this will move just the value 5 to the register R1. Okay. Or some other time, say for example, just now I told you that in this case, M is, let us assume, M represents this memory location 1000. Okay. 1000. M is 1000. This 1000 contains some value. We are not bothered about that. Say it is 20. Okay, now assume that I want this 1000. I want the 1000 to be moved to the register R2. Then what should I write? I should write move R2 comma hash M. Okay, hash M, hash. So hash represents immediate value. So hash means it will not take the value of M. It will take what is M. What is M? M is 1000. So that 1000 will be moved to R2. Are you getting? So this also comes under immediate addressing mode. Okay, but if you use just move R2 comma M without hash, then it will move that this 20 to R2. Then it will take the content. Okay, but here we don't want the content. We want this address, which is the immediate value. So in that case, you have to use hash. So now it means M is something like a variable we are using. But if you give the value directly, then you can directly give like this, move R1 comma 5, right? So this type of addressing comes under immediate addressing mode. Next is register addressing mode. Here we directly specify some register name. Say example, move R1 comma R2. So it will just move the content of R2 to R1. Okay, if R1 contains 5 and if R2 contains 10, now the content of R2 will be moved to R1. That is, the old content of R1 will be overwritten by the new content 10, whereas the content of R2 will be the same, that is 10, right? So this type of addressing is called as register addressing mode. So both operands are specified through a register. In immediate addressing mode, one of the operand will be an immediate value. In implied addressing mode, one of the operand will be implied. That is, it will not be specified, but based on the instruction, it will be understood. Fine. So next, what we will be discussing is indirect addressing mode. So this is also called as register indirect addressing mode. So it is also called as register indirect addressing mode. When you say register indirect addressing mode, it means that I will explain this with an example rather than defining it. Let us take this example. Move R1 comma, we are not giving directly R2. Rather, we are placing this R2 within a bracket. Okay, we are placing this R2 within the bracket. Okay. So what does it mean? So when you specify R2 within bracket, okay, so what does that mean in the sense? In the sense, R2 contains some value, right? Let us assume R2 contains value 3. If R2 contains 3, it means that it is referring to register 3. It is something we are using like a pointer. If R2 holds the value 3, okay, if R2 holds the value 3, that means that we are using R2 as a pointer. Pointer to where? Pointer to register 3. It means R2 is pointing to this register. Okay, it means R2 is pointing to this register, which is R3. And now what is R3? what R3 contains? 5. So that 5 will be moved to R1. That is the meaning. That 5 will be moved to R1. Are you getting? So this is a pointer which is pointing to R3, and R3 contains the value 5, and that will be moved to R1. So this type of addressing is called as register indirect addressing mode. Okay. So instead of using register here, we can also use memory. Instead of using register here, we can also use memory. For example, say I am using like this, move, then that memory location will act as a pointer. Move R1 comma, say LOC. So anything other than R0 to R9 will be treated as some memory locations, even if you give A, B, C, all those things, right? So say okay, LOC, right? Now let us assume that LOC is some address. This is C, right? Say LOC is some address in the memory. Okay. Say this is LOC. The location LOC is this. Say the address of LOC, let us assume it is 1000. Okay. So it also works in the same fashion. When you give move R1 comma R2, what does it mean? R2 acted like a pointer. Similarly here LOC will act like a pointer. Let us assume LOT contains 2000. Then it means that this LOC will now act like a pointer. It means that LOC is pointing to the address 2000. So at some, there will be some address 2000. Okay. If this address 2000 contains the value 15, then it will move that 15 to R1. Now R1 will become 15. Okay. Right. So this is called as memory indirect. Okay. So it can be either register indirect or memory indirect. So when you give register indirect, it points to some other register, whatever the depending on the value, and it acts as a pointer to some other register. If you give some memory location, it will act as a the value you give here in that particular right hand side within. So it will act as a pointer to some other address, and the value from that address will be fetched. Okay. So this register indirect mode is specified by using this bracket. Okay, when if this bracket is not there, here if the bracket is not there, then it becomes the direct addressing. Okay, that is it becomes a register addressing mode. Okay, register addressing mode. Okay, so this is how the register indirect or the just indirect addressing mode works, right? So you may ask where should we use this indirect addressing mode? So in that context, here is a program. Here is a small program which explains the applications of register addressing mode. Okay. Let us assume that we want to add some sum of n numbers. Okay. Consider these numbers are stored in some memory location. Assume these numbers are stored in some memory locations, starting from the location num1 to say the numbers are stored in the location starting from num1 to numn. Okay, we want to fetch all these numbers and we want to add, right? So numn. So that is, we want to find the sum of the numbers from num1 to numn. Okay, how to do that? That's what we are going to discuss. Okay, say how many numbers you want to add. That is available in another location. Let us call that location as n. Okay, for simplicity, let us assume n is 5. Okay, then what this statement does, move n comma 5. So it will move the value of, it will move n comma r1. Okay, move n comma r1. So what it does in the sense, it will move the value at location n to the register R1. So R1 will have now 5. Okay, R1 will have now 5. Okay, so it can be either move n comma R1 or move R1 comma n. Okay, so that depends on the programming language. So here we discussed that it is moving in this direction. Okay, so let us assume this is R1 comma n. Okay, move R1 comma n. Okay, for our understanding, move R1 comma n. Okay, so it moves So it moves so I'm writing like this just to follow one format. So move r1 comma n, it moves 5 to the register r1. Okay, it moves 5 to the register r1, right? Now move hash num comma r2. Okay, again, okay, or let us understand this way itself. Let us, uh, but I think you are clear. Move n1 comma r1 means it moves the content of n to r1. What is n? 5 is moved to r1. Okay. Again move hash num1 comma r2. What is hash num1? Let us assume num1's address is 1000. So hash, I already said, it will give the immediate value. It won't give this value at location. Rather, it will give the immediate value. That is 1000. So 1000 is now moved to R2. So R2 will hold 1000. Okay, that is the address of the first number, right? Then clear R0. The register R0 is set to 0. Clear R0 means the register R0 now it is set to 0 because it may have some garbage value that we are clearing. Because here only we are going to store the sum of all these numbers, right? Okay. Now what we are doing, add R2 comma R0. Here you see R2 is specified as what? R2 is specified in what style? It is specified in what you call register indirect style. It is specified in register indirect style, but we are moving in this direction. R2 and R0 will be added and the result will be stored in R0. Okay, the result will be, so R2 is not, it's not a, whatever R2 contains, that represents a memory location. Okay, what R2 now contains? What R2 contains? R2 contains 1000. R2 contains 1000. Okay, so it means it is referring to the memory location 1000. So it is indirectly referring to the location 1000. So it is acting as a pointer to the location 1000. Okay, so the value at this location, say if the value at this location is 1, that will be added with R0. What is R0? That is 0. So it will do 0 plus 1 and the result will be stored in R0. Okay, fine. Then what we are doing, add hash 4 comma R2. Why we are adding 4 with R2? Because we are assuming that the computer is a what you call, the word size is 32 bit. Okay, the word size of the computer we are assuming to be 32 bit. So 32 bit means what? 4 bytes. 32 bit means it is it's a 32 bit word size, so that is 4 bytes. Okay, so we are not adding 1, we are adding 4 to R2, right? So next, previously what is R2? 1000. So when you add 4 to R2, it will point to the byte 1004. That means the next value is stored in the location 1004. The next value is stored in the location 1004. Okay, so say the next value is 2. Okay, so now R2 is holding 1004. Then what we are doing, decrement R1. Decrement R1 means previously R1 was 5, now R1 will become 4. Then you are checking branch greater than 0. That is, you are checking whether the previous arithmetic operation, which is a decrement, does it result in a value greater than 0? Yes, it's greater than 0. If it is greater than 0, loop. That means go to this instruction. Which instruction? Again add. Again add R2 comma R1. That's R2 is a pointer. Now R2 is pointing to where? 1004. What is 1004? 2. So add 2 with R0. What is R0? Already it contains 0 plus 1. To that you add 2. Okay, right? Again add 4 to R2. Now R2 will become 8. 1008. So it is referring to the location 1008. Okay. Again decrement R1. Now R1 will become 3. Again check, is it greater than 0? Yes. Again loop. So like that it will continue. So like that it will add all the 5 numbers. Okay, 1, 2, 3, 4, and let us assume each location contains these numbers 1, 2, 3, 4, 5. Once all the 5 numbers were added, okay, once the 5th number is added, Then when you decrement, R1 will become 0. Then it will check whether branch greater than 0. No, it's not greater than 0, it's equal to 0. So this instruction will execute. Move R0 comma sum. Again, sum represents some memory location. Say this last location represents sum. So here the sum of the value will be stored. 5 plus 4 9, 9 plus 3 12, 12 plus 2 14, 14 plus 1 15. So that will be stored here. Okay. So this is a simple example like where the register indirect addressing can be used. Okay. So this whether the result is stored in the left side register or right side register, that depends on the type of the processor. Okay. In this example, what we discussed, it is stored in R1. Okay, R2 is acting as a pointer, and whatever R2 points, that value is fetched and it is stored in R1. But here it is in the different way. It is storing in the right hand side. Okay, that depends. Okay, and it is not that the register should always point to another register. It can also point to a memory. So here we discussed that R2 is pointing to another register R3, but here R2 is pointing to the memory location, right? Okay. Actually, generally we use this addressing mode to make the registers point to the memory, right? Okay, fine. So this type of addressing is called as register indirect addressing mode. Next is direct addressing mode. It's very simple. Here we directly give some address location. So move, example, move LOC comma R1. The content of R1 will be moved to the memory location specified by LOC. If LOC represents the address, say 3000, and if R1 contains the value say 72, then that value 72 will be moved to this location. Okay, so this is called as direct addressing, because directly we are specifying the address. Okay, no indirect or nothing implicit. Okay, so this is called as direct addressing mode, right? Whereas in the previous case, the address is represented through the registers. Okay, so that is called as indirect addressing mode, right? Fine. So next we will discuss the addressing modes which is related to indexing. Right? Fine. So this addressing mode is called as index mode, right? This is called as index mode. Here the effective address of the operand is generated by adding a constant value to the content of the register. Okay, this is the definition. Here the effective address is calculated, effective address of the operand is calculated by adding a constant value with the content of a register. Fine. So what is that? Let us try to understand that. Okay, so this is an instruction. Let us assume this is an instruction, uh, uh, x of R1. So what is this x of R1? So it means that Ri represents some register, or x of Ri. So Ri refers to some register. Okay, it may refer any registers from R0 to, it may refer any register from R0 to what you call or n. Okay, it may refer to any general purpose register. Okay, where x is a constant, where x is a constant. Okay, so this addressing mode, what it will do in the sense, when you give something like this x of Ri, when x of Ri appears in some instruction, say not say it's something like this, say add what you call add or not comma 10 or 10 within bracket R1. Okay, so what does it mean? So see, this 10 is a constant. Okay, that is what here x. Okay, this Ri is some register. Okay, here we have given Ri within bracket. That means what? Forget about this part. Here we have given Ri within this bracket. That means it is a indirect addressing mode. It means R1 is referring to some address. So if R1 contains 2000, if R1 contains 2000, it means it refers to the address 2000. Okay, it refers to the address 2000. Okay, So this 10 what it is saying, in the sense, add 10 to this R1. So R1 is 2000. When you add 10 to this R1, it becomes 2010. So it means that now it is actually referring to the location 2010. Okay. So it says that add the content of this 2010 with R0. If R0 is 5 and 2010 contains 7, then it will add 7 plus 5, 12, and the result will be stored in R0. Okay, fine. So this is how this particular addressing mode, index addressing mode work. So normally we use this for accessing arrays. Okay, because say for example we are storing array values from 2000 to 2010. Then initially I want to add all these things. Then I will say add of R0 comma 0 comma R1. Okay, that is the content of 2000 will be added with R0. Then the next instruction I will say add R0 comma 1 comma R1. Now what will happen? R1 is 2000. The value at 2000 plus 1 is 2001. The value at 2001 will be added with whatever the content of R0. Then the next time, so this is add repeating. Okay, so next time add R0 comma 2 comma R1. So R1 is 2000, 2000 plus 2. The value at 2002 will be added with the existing content of R0, and the result will be stored in R0. So it means that now we have added the content of 2001 with 2000 with 2001 with 2002. Like that we can keep on adding, right? Okay. So here I assumed byte addressing, but generally it won't be byte addressing. If the word size is 32-bit, then we, instead of 1 it will become 4, and this will become 8, so on and so forth, right? So this type of addressing is called as indexed addressing mode. Let us discuss this with an example. Okay. So here is an example. You can see it is add 20 of R1 comma R2. Okay, 20 of R1 comma R2. So what it does in the sense, see, in this case R1 contains 1000. R1 contains 1000. Okay, so 1000 it refers to some address. 1000 actually refers to some address. This 20, this constant, we also call it as offset. This 20 is called as constant or offset. Okay, so here offset is given as the constant. Whatever you give in the directly, that is called as constant. Okay, so what it will do, it will add 1000 with 20, that is 1020. 1020 is this location. So it means that operand will be fetched from this location. The value at this location will be added with R2. Okay, and the result will be stored in R2. Okay, here in this case, right, and the result will be stored in R2, right? Okay, so it is not that always you should specify the offset as a constant. Even you can specify the base address as a constant. Here you can see add 1000 of R1 comma R2. Okay, here now what is R1 value? 20. Okay, that is offset is given in the register. Okay, now offset is specified in the one of the general purpose registers or index registers. Okay, whereas address is given as a constant. Okay, both will do the same job. Here what we are doing, add 1000 of R1 comma R2. What is 1000? 1000 is 1000, R1 is 20. 1000 plus 20 is 1020. So the value at 1020 will be fetched, and that will be added with R2, and the result will be stored in R2. Okay, so the point is it can be either way. That is, either you can specify offset as a constant, or you can specify address as a constant, right? Fine. So let us further try to discuss this with one program. Okay, so let us assume that the marks of n students were stored in memory location. Okay, for each of the student we are storing 3 marks: the marks of test 1, the marks of test 2, and the marks of test 3. Like that we are storing the details of n students. Okay, we want to sum up all the marks of test 1 of all students. That is, test 1 marks of first student should be added with the test 1 marks of second student. That should be added with the test 1 marks of third student and fourth student, so on and so forth. So what is the total sum of test 1 marks? And what's the total sum of test 2 marks? And what's the total sum of test 3 marks? Like that we want to identify. So how can we do that with an assembly language program? Let us understand, right? So this is the memory structure. So the memory location n, it contains the number of students details, okay? And this list, this contains the ID, student ID of the first student. Okay, this contains student ID of the first student. So here we are assuming the computer is a word, is a 32-bit word size computer. That is, each word occupies 4 bytes. Okay, so the test 1 marks of the first student will be in the location list plus 4. So list contains the starting address of the first student's student ID. So list 4 will have, list plus 4 will have the test 1 marks of the first student. List plus 8 will hold the test 1 marks of the test 2 marks of the first student. List plus 12 will hold the test 3 marks of the first student. Okay, because each word occupies 4 bytes, so there is a gap of 4, right? 4 plus 4 8, 8 plus 4 12. And list plus 16 will hold the ID of the second student. So what will be this? This will be list plus 20. Okay, the test 1 marks of the second student will be at list plus 20. What will be this? List plus 24. The list plus 24 will hold the test 2 marks of the second student, and this will be list plus 28 will hold the test 3 marks of the second student, so on and so forth. So the student ID of the third student will be in the address list plus 32. The student ID of the third student will be in the address list plus 32. Okay, it continues like that. So if this if the data are stored like this in the memory, then how can we write a program using indexed addressing mode? That's what we are going to discuss. Okay, so this is the code. Okay, so first what we are doing, move hash list comma or not. So hash represents immediate value. Okay, so let us assume this is, so this is list, it refers to this address. So let us assume this address as 1000. Okay, 1000. So hash list represents this 1000. Okay, so that 1000 is moved to or not. So now or not contains 1000. Now or not contains what? 1000. Okay, then what we are doing, clear R1, clear R2, clear R3, because we want to make 3 sums. One is sum of all test 1, sum of all test 2, and sum of all test 3. Sum of all test 1 we are going to keep in R1, so we are clearing this R1 to 0. Sum of all R2 test 2 we want to keep in R2, so this also cleared to 0. Sum of all test 3 we would like to keep in R3, so this also cleared to 0, right? Then what we are doing, move n comma R4. Okay, let us assume for a simplicity case n is 5. We have 5 students for whom this sum should be done. Okay, so n is 5, so n comma R4, so it means R4 contains the value 5. Okay, R4 contains the value 5. Okay. So next what we are doing is next what we are doing is, now we are applying indexed addressing. Okay, add 4 of R0 comma R1. R0 within this bracket, it means it's an indirect addressing mode. So R0 R0 contains what? The register R0 contains 1000. So it means it is acting like a pointer. So it is referring to the location 1000. Okay, and that 1000, okay, 1000. So it is referring to the location 1000. 1000 is added with 4. 1000 plus 4 is what? 1004. So the value at 1004, value at 1004 is what? So if this is 1000, then this is 1004. Value at 1004 is nothing but the test 1 score. Okay, say if the test 1 score is 89, then take that. Okay, that will be now kept in R1. Okay, R1 will contain what? 89, which is the test 1 score of the first student, right? Then what we are doing, add R0 8 comma R 8 within bracket R0. What is R0? We are not changing this R0. R0 is still 1000. 1000 plus 8 is 1008. What is 1008? That contains the test 2 score of that particular student, first student, and that is moved to R2. Okay, that is moved to R2. Let us assume test 2 score of the first student is 91. Okay, then add 12 or not. So that is 1000. Or not is 1000. 1000 plus 12 is 1012. So what is 1012? 1012 actually that contains the test 3 score of the. So this is, you can see, list is 1000, so it is 1012. It contains the test 3 score of that particular student. So let us assume of the first student. So let us assume that his test 3 score is 69. Okay, so what happened? So now the test 1 score of the first student is available in R1, test 2 score of the first student is in R2, and test 3 score of the first student is in R3, right? Okay, now the test 2 score of the first, test 1 score of the second student you have to take and you have to add with R1, like that you have to continue, right? Okay, so now we are adding add hash 16 comma or not. Now we are adding something to or not. We are adding what? 16 to or not. So or not is 1000. So 1000 plus 16 is what? 1016. Now or not is updated. Okay, here and all you are not updating or not. We are only here. R1 is changing. This is R2 is changing. This is R3 is changing. R naught is not changing, but here we are updating R naught. Now R naught becomes 1000 plus 16 is 1016. R naught becomes 1016. That means what? Which is 1016? 1016 is this. That is, now R naught is pointing to the second student. R naught is pointing to the second student, which is nothing but 1016. Okay, the ID of the second student, which is nothing but 1016. Okay, fine. Then what we are doing, decrement R4. R4 contains what? Number of students. Previously it is 5, now it becomes 4, because already we got the details of the first student. Then we check branch greater than 0. So the previous operation, does it resulted in something greater than 0? Yes, it's greater than 0. So loop. Again go back here. Again what? Add 4 R naught comma R1. Now what is R naught? 1016. 1016 plus 4 is 1020. What is 1020? This is 1020. Okay, this location is nothing but 1020, which contains the test 1 score of the second student, and that will be added with what? R1. R1 already contains 89. So if the test 1 score of the second student is say 87, then that will be added with that. Are you getting? Okay, next add 8 comma R naught. What is R naught? 1016. 1016 plus 8 is what? 1024. What is 1024? Again 1024 is this location, which refers to the test 2 score of the second student, which refers to the test 2 score of the second student. Okay, now that will be added with R2. What is R2? R2 already contains the test 2 score of the first student. Okay, so if this is 82, if the test 2 score of the second student is 82, then that will be added with R2. Okay, again add R naught 12 within bracket R naught. What is R naught? 1000. 1000 and 12 is what? 1000 plus 12 is what? 1012. So it is 1012. So what is in 1012? What is in 1012? The value in 1012 is the value in 1016 plus 12, right? It is 1016 plus 12. 1016 plus 12 is 1028. Okay, so what's the value at 1028? The value at 1028 is the test 3 score. The value of 1028 is test 3 score. Okay, so now that will be added with R3. So if the test 3 score is 78, that will be added with R3. Okay, again increment R naught by 16. So now R naught becomes 1032. Okay, that will be nothing but the student ID of the third student. Again decrement R4, it becomes 3. Again loop. So this process continues until you calculate the sum of the test 1 and test 2 and test 3 marks of all the students, and the sum of all test 1 will be stored in R1, sum of all test 2 will be stored in R2, sum of all test 3 will be stored in R3. Okay. And finally, what we are doing, when it becomes 0, the loop will not go there, rather these following statements will execute. All that sum of test 1 is moved to sum 1, all the sum of test 2 is moved to sum 2, all the sum of test 3 is moved to sum 3. Okay. So this is how this particular concept works, right? Okay. But there are some variations of index addressing modes. As in the first table we discussed, there are 3 types of index addressing modes. So what we have discussed is only one. This is the basic index addressing mode. There is another, there are 2 more variations of this, which is, the first one is called as base with index addressing mode. Here, instead of specifying one constant and one register, you can specify both as registers. So that type of addressing is called as base with indexing. The basic version is called as index addressing mode, where one value will be specified as a constant and one will be as through the register. Whereas in base with indexing mode, both values can be specified through registers. Here you can see one is a constant and one is a register. But instead, if you modify this instruction, like instead of this, if I write like say R6 comma R0, R6 comma R0. Okay, then what does it mean? R6 will be added with R0. So R0 is 1000 plus R6, that is R6 should contain 4. So let us assume previously we are moving 4 to R6. Move R6 comma 4, immediate value 4. Okay. Now what it will do, R6 will be added with R0. R0 is 1000. 1000 plus 4 is 1004. Okay. So 1004, now the value at 1004 will be moved to R1. Right? Okay. So this type of, if you use like this, that is called as what? That is called as base with index. This is called as base with index. If you use directly, that is called as index. Okay. Again here we can increment or once again we can say add what do you call, add R6 comma 4, add R6 comma or add 4 comma R6. Okay, our result is going the right hand side as of these programs. Add 4 comma R6. What it will do? It will add it will add 4 with the content of R6, and the result will be stored in R6. Already R6 contains 4, so now R6 will become 8. Okay. Then this instruction also you can change. Here instead of 8 comma or not, you can say R6 comma or not. You can say R6 comma or not. Okay. What is R6? R6 contains 8. R0 is 1000. So 1000 plus 8 will be the value at 1000 plus 8, that is 1008. Whatever the value at location 1008, that will be added with R2 and the result will be stored in R2. Okay. If you use like this, then that is called as base with index addressing mode. Right? And there is another variation which is called as base with index and offset. Here we give 3 things: x of Ri comma Rj. That is for example, say this instruction, what it is, yeah, say add, let us assume add 4 within bracket, say R6 comma R0, okay, comma R1. So what it will do? So as usual, let us assume R1 as 1000. Okay. The recent value of R6 is 8. Let us assume it as 8. Okay. So it means R1 is 1000. 1000 plus 8 is 1008. To that it will add this 4. Okay. 1008 plus 4 is 1012. So the value at location 1012, whatever the value at location 1012. Okay. If the value at location 1012 is say 74. Okay. And if R1 contains 8, then 74 will be added with 8. 74 plus 8 is 82, and the result that will be stored in R1. Okay. So there are 3 things here. We are adding 3 things. So if you want to do something like that, then you should use base with index and offset. Okay. So there are three ways of indexing. One is basic indexing, next is base with index, next is base with index and offset. Right. Okay. So the next addressing that we'll be discussing is relative addressing. So here relative means it is relative with what? It is relative to program counter. It is relative to program counter. That is, normally the program counter will contain the address of the next instruction to be executed. If you want to execute some other address which is not being pointed by the program counter, and maybe the address which follows the program counter, or the address which is 4 locations away from the program counter. Okay, in such cases you have to use relative addressing mode. Okay, that is, whenever you want to access some locations which are n locations away from the programming counter. Okay, we can generalize like that. If you want to access any operand which are n locations away from the programming counter, then you can use relative addressing mode. So this is also similar to the way of working is similar to indexing. Okay, we are giving x of PC. So x is some constant. So this constant will be added with the content of PC. As a result, whatever the address you are getting, the value at that location will be accessed. If PC is 2000, okay, and if x is 8, then 2000 will be added with 8. Then you got the address 2008. Okay, now the value at the location 2008 will be accessed. Okay, so this type of addressing is called as relative addressing mode, right? Okay. So this diagram just shows how relative addressing works. Okay, so if the program counter contains 2, okay, program counter contains 2, and the constant, whatever the relative address, the constant RA stands for relative address in the reverse order. Okay, address relative address. If the relative address is 100, then it will add that both 100 plus 2 is 102. So the data available at the location 102 will be fetched. Okay, so this is how the relative addressing mode work. Okay, so it is relative with respect to program counter. Fine. So there are some additional addressing modes which are like increment and decrement, auto increment or auto decrement. So auto increment works similar to something like a post increment, that is, it will increment after performing the operation. Okay, whereas we also have auto decrement which will decrement first. Okay, so here also if you put this plus before, then it will perform increment first and then perform the operation. Here also if you put the minus at the other end, it will become post decrement. Okay, it will first perform the operation and then decrement. Okay, so here is a simple program which is given which uses the auto increment. Okay, I think it is again the same sum of the adding n numbers, right? So let us see. Move n comma r1. So n is some constant. How many numbers you want to add? Say n is 5. Let us assume n is 5. So 5 is moved to r1. Move hash num1 comma r2. Hash num1 contains a starting address, that is moved to r2. So if we want to add some 5 numbers, these numbers are stored at address 1000. Okay, these are stored at address 1000, 1004, 1008, something like that, right? Clear R0. The final result should go to R0, so we are clearing R0. Okay, add R2 plus R1. R2 we are giving R2. See, R2 we are giving within this bracket and then plus. So it means what? It is a indirect addressing mode. It refers to that address. So 1000 contains some value. Okay, say 1000 contains so this location 1000, what it contains. Say it contains, say this is location 1000. Say it contains some value. Say it contains 2. Then 2 will be added with R0. Okay. After that, R2 will increment. How much it will increment? That depends on the word size of the computer. Okay. If the word size is 1, it will increment by 1. If the word size is 2, it will increment by 2. Okay. If the word size is 4, that is 32 bits, it will increment by 4. The increment that depends. Okay, fine. So as we discussed previously, the word size of 32 bits, let us assume it is incremented. So after adding, it will increment. What will increment? R2 will increment. So now R2, the new value of R2 will be 1004. 1004. Okay, again we are decrement. Next is decrement R1. So now R1 will become 4. Again we check whether branch greater than 0. Yes, the previous arithmetic operation resulted in a value which is greater than 0. So loop. Again go here. Again add R2 with R0. What is R2 now? 1004. What is in 1004? What is in location 1004? So each word occupies 4 bytes. So 1004 says 7. So now 7 will be added with 2. Okay, that will be stored in R0. So previously R0 contains 2, and now 2 plus it will become 7. Okay, and after that R2 will increment. So R2 increments by 4 because the word size is 4 byte. So it will become 1008, right? Now once again it checks whether branch greater than 0. Yes, loop. So like that it will add all the numbers. Finally, after adding all the 5 numbers, this will become 0. So this branch, now it won't work. Now move R0 comma sum. The final result will be in R0, that is moved to the location sum. Okay, sum refers to some memory location. Okay, maybe one of the memory location here is given the name as sum. Okay, maybe it refers to some address, say 3000. Then whatever the final result, that will go here, right? Okay, fine. So that's it about the different addressing modes which we are using, right? Okay, let us stop here. Thank you.